let me see the plan for the day. And as you can see on the ELMS, there's several review review worksheets has been given out by Dr. Chadwick. So today I'm going to give you the first half of our review for the coming exam. And I'll be talking about the review examination 4 review, Mass 141, May 2020. So let me actually share the screen so that everyone can see that. So you should all be able to see my screen right now on the PDF version of the exam I'm going to review today, which is this one here, okay? Anyone has a trouble seeing everything like this, seeing my screen here, the shared screen? Okay, let me see, what's the question? Okay, perfect. So let's begin. So today I'm going to give a quick review of the 4 questions here, and also there are several other questions I'm going to review also. So let me see the participants. Let me see my screen. So do you guys actually have this exam available on your computer?
Where would it be? Would it be on the ELMS page?
I think so. Or I can just send to you guys quickly right now, actually. But why don't you just take a screenshot of what I have here, and so I can cancel that and can see my other screen for writing everything on the paper, actually. Okay, can you guys do that? Just take a quick screenshot of the review exam I'm going to do right now, and I'm going to also roll over to number 3 and 4. So this is number 3 and number 4. Okay, everyone's good. So I'm going to stop sharing the screen. I'm going to begin writing on my paper pad, and so that I can start reviewing this thing. Okay, 3, 2, 1. Okay, so let's do that. So today I'm going to review the exam 4, and also there's another review worksheet that Dr. Chadwick has been sending to me, and hopefully I can cover some questions from there too. So let me begin with the first one here. The first question I want to do actually is this one. Is the geometric series question. Okay, the typical example is the following one. So the one on the exam is given by n equals to 1 to infinity, 2 to the nth power, minus 3 to the n plus 1th power over 4 to the nth power. Okay. If you read the question carefully, the question says, find the value of the series. Okay. So whenever you see something like that, find the value of the series, that means it's converging implicitly, right? It's implying that the series already is converging, and your job is to find out what's the value of this series, right? So from the question, we know it's converging based on the statements, and our goal is to find out what's the value of these. To do this one, we begin with some manipulations. The key observation here for this question is that you can never write this whole series as one individual geometric series. Actually, you should be breaking this into 2 pieces, and each piece will be a geometric series, and they are different. Okay. So for example, you get the following. The right way to do this is by splitting this into these 2 pieces. And you can see almost immediately that these are 2 different geometric series, because for the first one, the R value for this geometric series is given by 2 over 4, right? That should be clear. Whereas for the second geometric series, the ratio R is given by 3/4, which is different from the first one, right? So the value of this will be, by my formula here, is initial term over 1 minus R is my summation for everything here. So what's the initial value for this is given by n equals to 1. So that corresponds to 2/4. That's my initial value. Over the ratio here is also 2/4. So it's 1 minus 2/4, right? That's my first one. And the value for the second one is, what's the very first term is given by n equals to 1. That corresponds to 3 squared over 4, which is my first initial term of the geometric series. And my ratio R here is just 3/4, right? So everything can be then reduced into, I guess, 1 minus. This is actually 9/4
Sorry, Bo, could you move the
over 1/4
right
that equals to actually -8. Sorry, what's the question?
Could you move the paper over to the right a little bit, please?
Okay, like this.
Thank you. Yeah.
Yep. Sorry. Let me shift to the.
Just want to make sure I'm not missing anything.
Okay. Yeah, sure, no problem. Okay. Can everyone see that clearly? Okay. Okay. So you see that the idea is, first of all, you should be able to recognize the different geometric theories contained in this expression here. Okay, there are 2 different geometric theories. So the right way is to split them up into 2 pieces, and each of them have a different R value, and they correspond to 2/4 and 3/4 here. And the formula we are using actually is the series, actually the sum equals to this. This is the formula we're using here implicitly, okay? And the initial value is given by the initial value here correspond to index n equals to 1. So that's why I get n equals to 1 for this term is 2/4. The n equals to 1 here correspond to 9/4. Hence the value is -8 for the summation here, okay? And that's how you solve this problem here. And the next question is a different question. Let me have it here. So let me write down a similar question. A similar question will be n equals to 1 to infinity, 3 to the n plus 2 to the n plus 1 over maybe 6 to the n. Okay. And then you could see that actually this is very easy to see, right? I mean, very similar to this case. This is not a geometric series on its own, right? This is not a one single geometric series. That's what I mean. But it can be split into 2 different geometric series summed up because of the summation here, right? So the right way to do this is to sum up n equals to 1 to infinity, 3 over n over 6 to the n, plus summation n equals to 1 to infinity, 2 to the n plus 1 over 6n, right? And then you should be able to recognize what is R value in this case and what's the R value in this case. And this will be a very simple application of the previous formula, and you get something like this, right? So I won't be writing down the value for this, but you see the idea, right? I mean, this is pretty straightforward. So knowing how to play with one single expression and split that into 2 different pieces and recognize a different R value and recognize the different initial terms are the only thing that needed for solve this kind of question. So there's nothing more than that. One particular fancier question would be if I have maybe 3 to the 2n plus 2, let's see, minus n plus 1 over 6n summation n equals to 1 to infinity. The only thing that you have to be careful about is that in this case, it's no longer for the first piece, which when you write it like this, let me ask you guys, what's the R value for this first piece? What is R in this case?
Is it 9/6?
9/6, yes. And the R value for the second one is given by, because of negative sign here, you should think about this as 1/2 to the nth power, right? So the R value in this case is 1/12. Does that make sense?
Yeah, where did you get this square from? Like 2/6. Why is it 2/6 squared, but 3/6 isn't squared?
That's because the 2 here. So here's the logic here is that the 3 to the 2n over 6 to the n is the same as 3 squared to the n over 6 to the n.
Sorry, I meant in the previous one and the one before that.
Oh, that's because that's for the initial term. There's another 1 here. You still have the 1 here. That's not going to influence the R value, but it's going to influence the initial term.
Okay.
Yep. So for example, in this case, if I modify this to begin with 3, then what's the initial term would be n equals to 3 plugging into each of the term here. That makes sense?
Yeah.
So that would be 2 to the minus 3 plus 1, right? And 6 to the 3. So that's why you get this extra 2 here, or maybe minus 2 here in this case. That makes sense?
Yeah. Okay.
Okay. So how to deal with the extra coefficient here and how to deal with the extra adding constant here is another subtle part, but it's not difficult. It's just algebra. It's purely because of this. Yep. Okay. So perfect. I trust you guys knowing how to do this kind of question. So I'm going to move on to the next kind of questions, and which is about finding tailored polynomials for given functions. So for this, so the second question is I'm kind of jumping around, but still using the same line here. Yeah. So actually before that, let me do this following question: is let's determine if summation n equals to 2 to infinity n to the 4/3 plus 2n over n squared minus 3 converges conditionally or absolutely or diverges. Okay, so this is the question. We want to determine if this given series is converging conditionally, absolutely, or diverges. And to do this question, remember that what I mentioned to you guys is, first of all, we use which test? We use the nth term test or divergence test. Okay, let's see that. The first step, try divergence test. Okay, so in this case, that means we are going to evaluate what's the limit of these. The limit of these is n to the 4/3 plus 2n over n squared minus 3. Okay. And what is value for that? So when n becomes larger and larger, getting close to be infinity, I mean, moving to be very large, that's what it means to getting to infinity. If n is very large, then for the numerator, the dominating term is actually n to the 4/3, right? This is a larger exponent than the linear term, right? So this term contributes the most. Whereas for the denominator, n squared is a term that contributes the most. So the limit of this is roughly speaking equal to limit goes to infinity. Okay, let me have a parenthesis here indicating that this is roughly true, but you have to argue a little bit to convince yourself. But this is going to give you the right value for the limit. But here, since the numerator is still smaller than this, because this is a square growth where this is 4/3, rate of growth, right? It's completely determined by the exponents. So that's why this actually goes to 0, okay? So what this computation tells us is that if we try to use the divergence test, the limit of the nth term goes to 0, which means it's possible this one is converging. But we cannot argue from this computation to see this is going to be diverging, right? For this to be diverging, we need this to be something that's going to, for example, infinity or things like that, right? Very large. That's all. At least non-zero, right? But since it's 0, so this is inconclusive. Hence, it is inconclusive, meaning we cannot see anything. We cannot see anything. Okay. I mean, we still see something, but it's kind of useless in terms of determining convergence or divergence. But one crucial thing that we find out in this computation is that the series, the nth term, looks roughly like this, right? So at least they give us some kind of hint what's the next step, or to which series are we going to compare to, because since this is not a p series, this is not a geometric series. So that means we are going to use the comparison principle or limiting comparison principle. But to which series we are comparing to is indicated by this computation here, right? We are going to compare this one to a p series by the form of this expression here. Okay, so step 2. Compare it to summation n equals to 1 to infinity 1 over n to the 2 minus 4/3 equals to, I think, is 2/3, right? The reason why we are getting this because this actually is 4/3 over n squared. Okay, this is where we are getting this p series here, which is a p series. Okay. So you can see from this computation here, what's a p-value for the series is given by 2/3. That would mean that this series is converging or diverging in this case?
Diverging.
Diverging, yes. So that means this one is diverging. And now this is a scenario. We know that the series is almost comparable to this given p series, which is diverging. If we want to use the comparison principle, which direction of inequality we want? Do we want to see that this original series is smaller than something which is diverging, or we want to see that this is larger than something which is diverging? If you want to prove something is infinite, you better bound it from below by something is infinite, right? If you bound it from above, that means if it's smaller than infinity, you cannot say it's infinity. But if it's larger than infinity, it's going to be infinity for sure, right? That's the logic behind it. So if we're going to compare it to this one, we want this side, this kind of inequality. We want to see that is larger than this. This is the right inequality we want, right? But we cannot just simply put it there because you need to argue why this is true. And that's the whole point of this kind of comparison principle applications, right? You have to argue why this inequality is true. Okay. But that's not easy in this case. That's what I'm trying to say. So to use directly the comparison principle in this question is actually kind of hard, but still doable. So let me actually give you some hint how to proceed. It's because of following. Because this is always larger than n to the 4th power over n squared minus 3. Do you guys agree? If you make the numerator smaller, your fraction becomes smaller, right? If I forget about the 2n part, which is always positive, I'm getting something smaller, right? But if I make my denominator larger, I'm making the fraction even smaller. So if I forget about the -3 part, I get these. Do you guys agree? Okay. And this gives me 1 over n to the 2/3. Okay. And that means that's the reason why this inequality is true, because for term by term, each term on the left-hand side is always larger than the corresponding term on the right-hand side. Hence, we know that this series is always larger than this series here. But by p-test, I know this is diverging, right? So because we have these, and summation 1 over n to the n over 3 is diverging by comparison principle. The left-hand side, the left-hand side is diverging. Does this make sense? How I finished this problem? I first realized which series I'm going to compare to depending on the form of the expression. By the first computation using the divergence test, I see that even though it's inconclusive, I still get something, which is to which series I'm going to compare this one to is going to be this one, a p series. And the corresponding p here is 2/3, which means it's diverging. But then if I want to prove that, so that means heuristically, I know this one is going to be something that's diverging and comparable to this series. But how to rigorous everything is to have the right inequality like these. But to get this inequality is given by these two successive inequalities, right? By shrinking the numerator and by enlarging the denominator, I'm getting what I want, right? And then to finish the argument, I see that the following. Because I have the right inequality and because this is one diverging, then by comparison principle, the left-hand side, all the original series actually diverges. Does this make sense? Okay. So this is one typical application of the comparison principle. A different way to do this is to use the limiting comparison principle. Okay. A different way is to use the limiting comparison principle is the following. So if I want to use limiting comparison principle, I do the following. I look at limit when n goes to infinity of n to the 4th power 4/3 minus plus 2n over n squared minus 3 divided by the series I'm going to compare with. So in our case, it's 1 over n to the 2/3. Okay. Let me see that again. So if the limit of this expression is something that's 0 or finite, then that means these two series will be, if this one is converging, that means this one will be converging. But if the limit is something which is non-zero, that means if this one is diverging, this one will also be diverging too, which is the case. So let's compute that. I mean, but we know the answer. The answer will be 1, right? This is something that's very easy. You can get these. And because of that, that means the original series will be sharing the same converging or diverging property as a comparing series, which is diverging. Hence, this one is diverging also, right? So that's kind of logic. So if you write something like this on the exam and arguing using the limiting comparison principle, then you can get a conclusion without doing all this inequality thing here. You guys see the difference? Okay. This implies that summation n to the 4/3 plus 2n over n squared minus 3 and goes from 1 to infinity is diverging as summation n goes to 1, because is. Okay. Okay. Any questions about this question? Okay, everyone's good? So the next question we are going to work on actually is the following one, is to find if fx equals to 2 times x cubed times e to the x squared, we want to find the Taylor series about 0. And also we want to find the P8 of x. Okay. So this is the kind of question you will definitely have on the next exam. It's given a certain function, you're asked to find out what's the corresponding Taylor series and also the Taylor polynomial of degree 8 for this given function. Okay. And the way to do this question is, first of all, you need to know what's the corresponding Taylor polynomial or Taylor series for these three functions. Okay. So you should be able to write down the Taylor polynomial or Taylor series for this one, these three fundamental functions. I mean, given that you have a textbook with you on the exam, I guess this won't be a problem. So I'll assume that you guys can find it out on your own. Once we know this, then the question is, the new function fx is actually given by something that's built from these things. Okay. Except from this part, the 2x cubed term, which is a polynomial term, the only thing that you need to find out is a Taylor series for the exponential part by doing a substitution computation. And from there, you can multiply this term to it, and you get that. Okay, so let me write it down here for you guys. Fx equals to 2x cubed e to the x squared equals to 2x cubed. What's a Taylor polynomial for e to the x is given by summation and goes from 0 to infinity. X to the nth power over n factorial, right? But since we have x squared, so we just substitute everything x by x squared. Do you guys recognize these? Okay. So all I'm doing here is substituting x squared into the Taylor series expansion for e to the x. Okay, to get the Taylor expansion for e to the x squared. And from there, this is going to be 2x cubed summation n goes from 0 to infinity, and you get x to the 2n over n factorial. So I'm doing one extra step to simplify everything on the right hand side, from x squared to the nth power to x to the 2n. This is nothing but just algebra. Okay. The next step is that kind of the crucial step is, how do you merge this term inside the summation sign? There's no tricks. You just multiply this term by term to everything here. So you get n to the 0, n to infinity, and you have 2 here, and you have x cubed times x to the 2n. But what is x cubed times x 2n is x to the 2n plus 3 over n factorial. Do you guys agree? Any questions about this computation here so far? Okay, so this is how you finish this problem here. Okay, and that's the answer for the Taylor series expansion for this given function. Now to find out the P8, how would you do that? So P8 is a degree 8 Taylor polynomial. So the degree less or equal to 8 terms in this series. When will this degree be more than 8 correspond to n equals to, I guess, 3, right? That corresponds to 2 times 3 plus 3 equals to 9. So everything before n equals 3 should be included. That means n equals to 0, n equals to 1, n equals to 2. And that's only 3 terms you want to include in the P8. So that means you get 2 over 0 factorial times x cubed plus 2 over 1 factorial times x to the 5th plus 2 over 2 factorial over x to the 7. And that's all you have to write out as a power series, as a Taylor series, a Taylor polynomial of degree 8 for this given function here. Okay, because you can see that the next term will be x to the 9th power, which is not included in the P8, right? So this finished this problem here. So for this kind of question, I get 3 things. Knowing the fundamental model case, the exponential function, sine and cosine functions power series. Okay, Taylor polynomial or Taylor series. I mean, that's the same terminology. And knowing how to do substitutions and multiplications. And to find the Taylor polynomial, you're knowing where to truncate your Taylor series. And that's the easiest way to find the Taylor polynomial, is to truncate from the given Taylor series, which can be computed very easily. A different way to approach this question would be you honestly compute the first derivative, the second derivative, the fourth derivative, the 5th derivative, until to the 8th derivative of this given function, and find their value at x equals to 0, which will be the coefficient 1 divided by n factorial, and then you multiply by x to the nth power correspondingly. And that's the hard way to do this kind of question. But it's still doable, but not suggested. Okay. So this is the second question on the review exam I want to see today. Okay, and the third one is actually an alternating series. Okay, so we are interested in the following. Let me get some water first. So next question is about summation -1 to the nth power and n over n cubed plus 1. Okay. The question is, we want to see if this series is converging absolutely, conditionally, or diverges. Okay. But we see, first of all, this is going to be an alternating series, right? This is clear from the very beginning that this is an alternating series. So the criterion for this to be converging or diverging is simple, right? For it to be converging, we just need the nth term to be decreasing to 0, right? That's all we need to verify for this to be converging, right? But actually more can be said, because there are 2 methods. So to see this is converging, we need n over n cubed plus 1 to be decreased to 0, right? That's the thing we want. Is this true that n over n cubed plus 1 is decreasing to 0? Does anyone know how to solve this problem? To verify that this term. So this one definitely goes to 0. That's clear, right? Everyone with me? This one is definitely going to be 0 when n goes to infinity, because this is linear growth, this is cubic growth in the denominator. So clearly this goes to 0. But to see that it's decreasing is it's not very easy. Remember how I did that last time? Is by looking at the corresponding function fx equals to x over x cubed plus 1, and I compute f prime x, which equals to x cubed plus 1 squared times x cubed plus 1 minus x times 3x squared, which equals to 1 minus 2x cubed, over x cubed plus 1 squared. Okay, from this expression, you can see that the denominator is something squared. That's always going to be positive. The numerator is 1 minus 2x cubed. But remember, n, which is our x in this case, can only be larger or equals to 1. So everything here is smaller than 1, 0. 1x is larger or equals to 1, right? And that's the reason why this is decreasing also, because its derivative, which is the slope of the function, is always negative, meaning it's decreasing, right? So this is how you argue that it's decreasing and also goes to 0. So because these two conditions are met, that means this as alternating series is converging by the alternating series test. This implies that by the alternating series test, it converges. Okay. But by doing all these arguments, what we really get is that this tells you that this series is converging conditionally or absolutely. Can we say anything about that? We only know that the series itself is converging, but to see that it's absolutely converging or not, we need to look at the absolute value of the series. So let's look at the absolute value of the series, which is given by n over n cubed plus 1. Okay, when n goes from 1 to infinity. My question is, does this one converge or not? Anyone who knows that? If n over n cubed plus 1 is converging or not as a series? You guys should be able to tell it right now, actually, before the exam already. Any answers? Anyone who want to share some ideas?
Is it a p series because you can divide the n over n to the third to be n squared and that's greater than 1?
Yes, yes, that's very close. Yeah, so what you said is we can compare this one almost to summation n equals to 1 to infinity 1 over n squared, right? And the relation between these two is that this is going to be smaller than that, right? But you can see that the right-hand side, is this one converging or diverging? But in this case, the p actually equals to 2, right? So that means it's converging on the right-hand side. But because it's smaller than something which is converging, that means it's smaller than something that is finite. So that, excuse me, so the left-hand side here is also finite. Hence, it's converging. Okay, so we see that the absolute value of the original series actually is converging. So that means the series is not only conditionally converging, but actually it's absolutely converging. It is actually absolutely converging. Okay. Does it make sense how you get these? It's not only converging by itself, but its absolute value is converging, which is a stronger condition to see. And so that's why you see that this is absolutely converging. Okay. So a contrasting example I would see is the following. If you have minus 1 to the nth power 1 over square root of n goes from 1 to infinity. Okay, so this is the example. So this is a typical example where it's converging, but converges only conditionally, because this one is converging by alternating series test. But the absolute value of this, which is a p series, 1 over square root of n, is diverging because p is 1/2. So it's not absolute converging, but it's still converging by itself. Hence, this is a typical example of conditional convergence. Okay, so I want you guys to remember these two examples here and have a sense of what converging conditionally and converging absolutely means in different cases. So knowing examples is better than knowing definitions. Remember, these examples will tell you what these two concepts really means. Okay. Okay, so we are almost there. And then the next part of the question for this example is to find out, also we want to find out G, smallest G, such that the error summation n equals to 1 to j minus 1 to the n over n cubed plus 1 is within 1 over 10 to the series, sum of the series. i.e., we are going to use the error estimate for alternating series. Okay. So to do that, remember last time what I mentioned is that we write out the first few terms for the alternating series. So this series n equals to 1 to infinity minus 1 to the nth power n over n cubed plus 1 is like the following. It's going to be 1 n equals to 1. This is going to be minus 1 over 2 plus 1 n equals to 2. This is going to be a plus sign here. So this is 2 over 8 plus 1, right, which is 9 over 2 minus, what's the next term? The next term is 1 n equals 3. n equals 3 is going to be 3 over 3 cubed is 27 plus 1, 28, and blah, 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 okay, etc. And which term do we see is beginning smaller than 1 over 10? We need the next term, right? This is almost 1 over 10, but smaller than that. So the next term is plus 4 over 4 times 4 cubed. What is 4 cubed? 64 and 65, right? And the minus next time is 5 over 5 cubed is 125, so 126. Okay, so this is the series. And you can see here, this term is still larger than 1 over 10, whereas this one is already smaller than 1 over 10, right? So this is where you can cut. And the corresponding j will correspond to, this is j equals to 1, j equals 2, j equals 3, so this corresponds to j equals 3 here. And the smallest j, so that the next term is smaller than 1 over 10, is given by j equals 3. Okay. This tells you that j equals 3, the smallest one, such that the next term is smaller than 1 over 10. That makes sense? Okay. So all we are searching for is a term which actually is smaller than 1 over 10, but the previous term is larger than 1 over 10. That's going to be the smallest one that we are looking for. Because every other term afterwards will always be smaller than 1 over 10. So this is the first one that has this property here. Hence the smallest one. Okay? So this is how you solve a problem like this for the alternating series. And the next question is to find out, is to show that the series, this one. So let me do a different question. Actually, this one is kind of meaningless. Let me do a different one. Let's find out the following one. Actually, yeah. Yeah, let me just skip this one. I don't think this one actually matters. Okay, so let me skip this one. It goes directly to 4a, which is the following one. So we try to find the interval convergence for this series here. as a practice. So this will for sure be on the next exam. And let's see how we do this. I guess in this case, the only subtlety actually comes from the 2n part because of this 2 here. Okay, you have to pay attention to these. So how do we do that? We make the an, so let an be minus 1 to the nth power over n times 3 to the nth power times x to the 2n. Then an plus 1 over an, taking app's value, then equals to minus 1 to the n plus 1 times x to the, not 2n plus 1, but the 2 times n plus 1. So it's 2n plus 2 here, over n plus 1 times 3 n plus 1 over minus 1 to the nth power x to the 2n over n times 3n, taking app's value, okay, which equals to, in this case, actually it's equals to n over n plus 1 times 1 over 3 times x squared. Okay. Okay. So this is what you get when you take the app's value of the ratio using a ratio test. And we know that this one goes to, as n goes to infinity, the limit of the left-hand side actually of this expression actually goes to 1 over 3 x squared, right? So this is the limit. And we want this to be smaller than 1 in order to use the ratio test. Because if we want the ratio test to be valid, the meaning is converging, we want this limit to be smaller than 1. And from there, we know that x's value has to be smaller than √3 here. And this is the radius convergence here that we're computing. It's √3, that radius of convergence. So the next thing is to determine whether the boundary points are included or not. So the boundary points is given by the following. So we are going to look at x equals to √3 and also x equals to minus √3. Okay. When x equals to √3, you get alternating series. Which means it's converging there. I will omit the details, but let you guys to do that. But when x equals to minus 1, this is a p series with p equals to 1, that means it's diverging. So the interval convergence is actually the following. Is the answer. Okay. So I just skip the details for this testing on the boundary points to you guys. It's quite standard and trivial, but I will let you guys finish from there. Okay. Any questions for this one? The testing, the finding the interval convergence kind of question? Everyone's good? Okay. So then the next question I want to see actually is about, let's see, is to use a Lagrange remainder formula. Okay. But I will leave that to next time. Actually, I'll find some more examples on how to use Lagrange remainder estimate, remainder term estimate, to find the upper bound for errors next time. So for today, we're going to just working on these questions. And any questions so far on these examples? No questions? Everyone's good? Okay, so I guess in that sense, we just finished today's section, and I will see you guys on Thursday and keep reviewing from there.
Bye, Bo. Thanks.
Yep, bye. So make sure you work on the practice exams that Dr. Chadwick gave you guys. Okay, and yep, enjoy the lunch. Thanks. Bye.